Alrighty then. Um, where's this sign-up sheet, by the way? The attendance sheet? It's floating around somewhere? Yeah, pass it forward, if you will. So we said that the class of P and NP are both model independent. They're robust. They apply to any computation model. All the models that we know and love, Turing machines, Boolean circuits, DNA, cellular automata, and whatever else. So that's yet another reason for studying them. And we keep mentioning the $1 million problem. Literally, by the Clay Institute of Mathematics, they put a $1 million bounty on 7 different problems, and one of them is P is equal to NP. The Poincare conjecture, problem number 5, has already been solved. So, they are good for the money. Of course, that guy who solved it, Perlman, didn't care to collect the $1 million, which was kind of interesting. Not the easiest way to become a millionaire, but there it is. And it'll be there probably for a long, long time. If P is not equal to NP, it'll be a non-existence proof, non-existence of a polynomial time kind of algorithm for NP-complete problems. And that's part of the reasons why it may be so hard, because most experts in the field believe that P is not equal to NP. It's hard to imagine that it is, but we may be surprised one day. We don't know. It could be independent of the axioms. It could be one of those Gödel things that may be true but not provable. So it could be resolved in some strange way one day. But for now, it remains open. So there's a couple, several different types of reductions. The main two are many-to-one reduction, and that's the one we've seen before. We reduce something in A to something in B via some, function f, and a single instance of A gets reduced or transformed into a single instance of B, and it preserves membership and non-membership. And that's called a many-to-one reduction, because many things in A can all be reduced to the same thing in B. It doesn't have to be one-to-one. It can be many-to-one, as long as it preserves membership and preserves non-membership. But a different kind of reduction solves a problem A by multiple calls to a problem B oracle. So that's another way of reducing a problem to another problem, is if you had some oracle for B, you can solve A by multiple calls to B. And in the case of polynomial time, as long as you're calling B a polynomial number of times and B runs in polynomial time, then A is solvable in polynomial time. But this is not the same as that necessarily. It certainly has a different form, but whether NP defined this way or this way is the same class NP in both cases, that is still open. We don't know if it is or it isn't, actually. So we usually stick to this kind of reductions, to a one-shot kind of reduction, rather than call it many times in terms of the formal proofs. But both are valid to show that all of NP reduces to a particular problem. This is okay too. Yeah.
Does the number of calls to your oracle matter?
It better be polynomial. Yeah.
What if it's only is there a difference between one call and many calls?
That's a subtle question. So it could be that there's a difference between one call and 2 calls and 3 calls. These are all different complexity classes, slightly different than one another. We don't know that either, actually. Or more dramatically, whether a constant number of calls, the same as a polynomial, as a logarithmic number of calls, same as a square root number of calls, same as linear, same as quadratic. We don't know that either. We don't know if they're all equivalent. If calling it once or 10 times or 50 times, or calling it an unbounded number of times, as long as it's polynomial, all give you the same class NP. So it's kind of interesting. There's a lot of open questions about the type of reduction that you employ. There's like meta questions about P and NP. Is if you get still the same class, either way. But Richard Karp, when he wrote his famous paper showing a whole bunch of problems where NP-complete on the heels of Cook showing the satisfiability is NP-complete, he used kind of a many-one reductions, this kind of a one-shot reduction. But Cook, for some of his works, used kind of Turing reductions, calling an oracle potentially multiple times. But that's kind of a fine point. It's not a very, very significant point. And in practice, either one is fine. If you call it a linear number of times or one time, not that big of a difference as long as it runs efficiently. But theoretically speaking and technically speaking, it may not lead to the exact same class as the other. So that's what I'm saying here. It's still open whether they yield the same complexity class or classes. So this issue is not just about polynomial time, deterministic and non-deterministic polynomial time. They pertain to all of complexity theory, whether p is equal to p space and polynomial time is equal to logarithmic space, and whether exponential time and exponential, all these other problems that we saw that were open can be recast under the light of which transformation type you're using, and then you get potentially a different set of problems, slightly different because different transformation type may lead to slightly different classes, how you define it. So this is not just a PNP issue, it's permeates all of complexity theory. So there's a whole bunch of meta open questions right there. Okay. Any questions about that? Yeah.
So it's not known to whether or not co-production or co-production are equivalent.
Yes, we don't know that. We suspect they are. If you ask a bunch of experts who dedicate their life to this work and wrote theses and books about these topics, and you ask them, what do you really think if you had to guess? If you had to make $1 million bet or something, most of them will say, they're probably the same. But we can't prove it. So you can't be completely sure. Yeah.
If, in terms of reduction, could you say, is there a difference between having an NP oracle and having just solving the NP complete problem, or having an oracle for with an NP oracle? Are there different levels?
Yeah. So that brings an interesting question. Since you mentioned oracles, let me say something about the oracles. So back in the early 1970s, when Cook and Karp were doing their thing, showing lots of problems were NP-complete, and the whole theory was ballooning and gaining momentum, and a lot of interesting results were coming around, but they still couldn't prove whether P is equal to NP. And these were all computer scientists. So some of the mathematicians got a whiff of this problem, P is equal to NP. And some of the mathematicians, came into computer science and said, okay, look guys, nice try. We understand you have a tough problem that you can't solve, but you're not really mathematicians, we are. So step aside, children, we'll solve it for you. They kind of came in with this aura of, we know math, this is a math problem, so let us have a crack at it. And they tried. They failed. But they proved something very, very interesting instead. So it wasn't really a failure. It was a very interesting success, not quite on P is equal to NP, but something very related. So the mathematicians proved the following. Well, first of all, let me preface that by saying, since you mentioned oracles, an oracle is just a black box that you use to compute something else with calls to the oracle, and the oracle calls are free, constant time each, and you can call it, some bounded number of times, so the oracle doesn't cost you much. But now the computation is relativized to the oracle, is relative to the oracle. So it's a relativity theory of computation, where what it's relative to is this black box oracle that's fixed. And all the Turing machines have the same oracle attached to them. So you can have an oracle, for example, for sorting. It's sorting for free. Now what can you do and how fast can you do it? Other things now may drop in complexity because sorting is a free step now. You don't have to pay n log n anymore. It's constant time. So you can ask lots of computability, complexity question relative to a particular oracle. And you can choose your oracle, so that opens up a whole new set of possibilities. We already saw that if you have an oracle for the halting problem now becomes solvable instantly for free, but now there's a new problem that's undecidable. What is that problem? The halting problem for Turing machine with an oracle for the regular halting problem. The halting problem for this super machine now is undecidable for super powered machines. And certainly it's undecidable for regular machines. And it keeps going. So even if you have an oracle, some things remain very difficult or even undecidable, even if you have an oracle for an already undecidable problem for free. Okay, but you don't have to worry about decidability, undecidability. You can work these oracles at the level of polynomial time and non-deterministic polynomial time. So for example, if you could solve, matrix inversion or matrix multiplication for free, other things will become faster, but how much faster? And what will still be NP-complete, given that you can do hard problems for free within NP or P? So having said that, Here's what these mathematicians proved. That there exists an oracle for which, relative to which, P is equal to P. P is equal to NP. They proved that. Separately, they proved that there exists a separate, different oracle relative to which P is not equal to NP. Separately from that, they proved that there exists yet a third oracle relative to which NP and co-NP are equal to each other, but neither one is equal to P. They proved that there exist oracles for all the combinations that are not inconsistent, basically. How many understand what I just said? Okay, any questions about that result?
We've seen that before where someone proved that the oracle could exist with the one you just described.
We talked about oracles in the context of Turing jumps and Turing degrees, and we showed that there's infinite level of impossible problems, each one more impossible than the previous level, because even if you have an oracle for free for the lower level, there's still undecidable problems at that next level and so on. But we haven't talked about oracles at this level yet. We are now. So here's where it gets even more interesting. So whenever you have relativized computation and you attach an oracle, usually the same kind of proof or proof technique survives the oracle and is still valid with respect to the oracle, just with the oracle modification everywhere in the proof and in the result. We already seen an instance of that with a halting problem. We showed if you attach an oracle for the halting problem in the exact same proof as before, the whole proof still carries through, and you get an undecidable problem, the halting problem for these modified machines with the new oracle. So diagonalization survives oracle arguments, and so does dovetailing, and so does all these other techniques that we've been using, simulation and so on. Which means, because they found different oracles for which P is not equal to NP, P is equal to NP, P and co-NP, NP and co-NP are the same, but both are different than P. That means if you're going to ever show that P is not equal to NP, you couldn't use the previously used techniques, the known techniques that you used before, because now we know there exist oracles that can resolve that problem any which way you want. So that means if you want to show that P is not equal to NP using no oracle, or more precisely the empty oracle, the oracle that does nothing, it probably won't be a proof using diagonalization or dovetailing or simulation or any of the other techniques that we've seen and all the other known techniques, because most of these survive oracle arguments. In other words, if you attach an oracle, the proof still goes through and you get the same result. But because we get different results using different oracles, chances are it ain't going to be one of those techniques. Which means to prove that P is not equal to NP, not only it'll be very difficult, because the proof will be hard, you'll have to invent entire new proof techniques altogether, besides diagonalization, dovetailing, simulation, and all the other techniques, the pigeonhole principle, and the ones we've seen before, which kind of ups the ante even more. It's not a proof that the proof will be that hard, but it's evidence. Maybe there's some clever combination of techniques that we did use before that may work. But chances are it ain't going to be that simple. Just like Fermat's last theorem. When Fermat's last theorem was proven by Andrew Wiles back in '93, after 350 years of being open, it didn't just come up with a complicated proof. You had to invent entire branches of mathematics. You had to invent a whole new separate set of theorems and techniques, and finally then to use as tools to prove that Fermat's last theorem is true. Same for the Kepler conjecture about sphere packing. That the best way to pack spheres is like oranges in a grocery store, with the kissing number being 12. 12 spheres can touch a central sphere simultaneously at the same time. Whole new branches of mathematics were required to finally. So chances are Fermat didn't have that machinery. I mean, we're sure it didn't. It didn't exist back then. So we may need to develop whole new techniques of proof, not just another proof based on old techniques. Yeah.
So for the second one, the proof reduction, you have A, and is the B is the oracle for A, or is it for any NP-complete problem?
No, B is an oracle for the problem B. So A is one problem, B is another problem. So for example, this is, satisfy. This is the halting problem for Turing machines in polynomial time, or the behavior of Turing machines or whatever. This is satisfiability. And so B solves satisfiability, but A solves what non-deterministic polynomial time computations do or don't do, whether they accept or reject, and so on. So these are two different problems, or more specifically, two different languages. You could always couch a problem, quote unquote, as a language, right? So how would you couch satisfiability as a language, not just a problem? So the problem of satisfiability is I give you a Boolean formula, and you tell me if it's satisfiable or not. The language of satisfiability is all strings that correspond to satisfiable formulas, quote unquote, and the formula in between the quotes. And you tell me if that's a string in the language of satisfiability, which means you have to tell me if it's satisfiable or not, essentially. So it's equivalent, right? So any problem, quote unquote, could be couched as a language and vice versa. So, you think about languages and problems as interchangeable modulo these kind of representation issues. That's all. Any other questions? Okay, so, yep. Sure. Sure, there's an enumerator of satisfiable formulas. How would you enumerate satisfiable formulas? Let's go through sigma, all strings in sigma star, where sigma is the keyword alphabet. Right? For each one, first of all, check it's in the right syntax. The parentheses are balanced. A compiler can easily do. And for each one, check all possibilities. Write the truth table out for each one, and then you're spitting out satisfiable formulas and only satisfiable formulas. But each one of those will take exponential time to spit out because you'll be doing a lot of checking. So none of these problems in NP are undecidable. In fact, they're all perfectly decidable. Not only are they perfectly decidable, they're decidable within polynomial time. They don't even take exponential time to decide. So keep that in mind. They're all kind of within the decidable portion of the Chomsky hierarchy, right? So all of NP is within the decidable oval of the Chomsky hierarchy. The only problem is not even in that oval, it's outside that. It's in the recognizable but not the decidable portion of the Chomsky hierarchy. So yeah, you can write enumerators for all these problems. You can write an enumerator that will print out all Hamiltonian cycles of all graphs. But it'll take a long time to run. It'll be deterministic. And it's pretty straightforward to do. You can do it with a few dozen lines of code. Right? Just generate all possible permutations of the nodes. Each one is a cycle. And the ones that work, spit them out and keep going. And of course, you can enumerate all graphs, dovetail through all graphs, smaller to larger ones. For each one, find a cycle or determine it non-exists by brute force search. And yeah, you'll be printing out all Hamiltonian graphs, all graphs that have Hamiltonian cycles. So conceptually, all of NP is very easy to solve. If you didn't care about time. That's a big if. It's a big catch. There's nothing undecidable about any of it. But remember, at the beginning of the course, I said, first half of the course, we'll just worry about what's possible and what's not possible. Now, within what's possible, later in the course, we'll start splitting hairs about how quickly or slowly you can do the possible and not worry about the impossible anymore. Here we are doing that, as promised. Now we're splitting those hairs. And things are getting more subtle because it gets into finer and finer minutiae, and we have to watch the clock, how much time you're spending, how much space you're consuming. That's more tricky, difficult, onerous to do than just deciding whether it's doable or not doable, or not caring about resource consumption. All right, so 3-SAT. 3-SAT is just like SAT, except every clause has at most 3 variables and negations of variables. That's it. So it turns out that's NP-complete also. Again, conjunctional normal form. Conjunctional normal form means it's a product of sums, where product is and sum is ors. So why is that formula, a formula of that form, NP-complete? What makes formulas like that so difficult to guess? Because if you only had one SAT, in other words, formulas where in every clause, you had a single variable, only one variable in every clause. That's easy to determine whether a formula like that is satisfiable or not. How would you determine that if you only had one variable per clause? In other words, one big and. There's no ors even. If everything is so what's the algorithm again? So I'll give you a formula. How can you tell?
If every literal has, you can assign a truth value to any two. If no two literals have a conflicting truth values.
Yeah. So how would they be conflicting?
If one is true and one is not, like one is p and one is not.
Yeah. So if you have a variable that's x and another variable that's not x in the same formula, there's no way to satisfy that. Because if you make x true, that's true, but that's false. The not x is false. If you make the not x true, then the x is false. And it's an if and only if. So you have to look for a variable and its negation occurring in the same formula for every single variable. And it's satisfiable if and only if there ain't one of those conflicting pair. How many get that? And that's easy to check. How fast is it to check if you had to write a piece of code that does that? It'd be at most n squared, and if you do it more carefully, you'd probably do it in n log n pretty easily. And you could probably do it even in linear time if if you index the variables 1, 2, 3, 4, 5, because then you could just have a big array of size n, one per variable. Every variable you see is stored in the array, and if you see a negation of a variable, you go to the array and see if it's there or not there, and you'll know if you have a conflict. So in linear time, you can do this deterministically, no big deal. So one sat is easy to solve efficiently. Two sat, it turns out you can solve efficiently in polynomial time, but it's a trick. That's not easy to do. I mean, it's not too hard either. I don't want to discourage you. For extra credit, solve two sat in polynomial time. Three sat already is NP-complete. There's no hope for that in polynomial time efficiently. And we're about to prove that. And by the way, before we even prove 3 sat is NP-complete, why do we care about 3 sat, 2 sat, 1 sat, 4 sat, 5 sat? Why not just sat is NP-complete, end of story? Why do we split that hair? Yeah, so we're looking for the smallest kind of clause size that still explodes the problem out, NP-completeness wise, into a full bloom, difficulty of complexity for all of NP. And it's interesting to know where the threshold is. So for 1 sat, it's trivial. For 2 sat, not so trivial, but polynomial time. For 3 sat, the intractable explosion occurs. So it's nice to kind of find this threshold of intractability. It's kind of almost like a sensitivity analysis. Where does it blow up? So it blows up at 3, it turns out. It could have blown up at 7. Some problems blow up later. Some blow up sooner. But it's interesting to start splitting those hairs and see exactly where it happens. It's some sort of Occam's razor, too, kind of situation. You want to see what's the smallest, kind of simplest form of a Boolean formula that still has the full complexity of all of NP. And it's 3 sat. All right, the proof is not that hard. It fits in this last third of a slide. So for example, take this clause here that has a lot more than 3, 1, 2, 3, 4, 5, 6 Boolean variables. Convert it into a bunch of 3 clauses in a way that adds new variables, red, green, blue, and they appear like A naught, B naught. And this formula here, the converted formula, is satisfiable if and only if the first formula is satisfiable. Why? The first formula is satisfiable, like for example, if x is true, doesn't matter what the y and the z and w are. So if x is true, down here, x will be true. So it doesn't matter what the y is, and it doesn't matter what the a is, so make a false, which will make a naught true. But if a naught is true, it doesn't matter what the z is. And then you can make the b whatever you'd like, because it doesn't matter what it is either. So make the b false, then b naught will be true. So now this whole formula is true, so it doesn't matter what the u is, and make this, and it doesn't matter what the c is either, so make the c false, c naught will be true, and then the whole thing is true just because the x was true. So the truth of the x propagated out and made everything else true. How many see that? Good. Same thing if we made the y true, or the z true, or any other variable true. So I just proved that this is satisfiable if and only if this is satisfiable. But this is a 3 sat instance, which means 3 sat is NP-complete. Because if you have a formula with these kind of clauses, convert it to these kind of clauses, and if you have a solver for this, you automatically have a solver for that. And so all of NP reduces to 3 sat. Now, why is all of NP reduces to 3 sat? I just showed that this reduces to 3 sat. What about all the rest of NP? All of NP reduces to that already. That's Cook's theorem. And now this reduces to this. So now compose these two reductions, and all of NP using the composition of Cook's theorem plus this reduction will reduce all of NP into 3 sat, not just sat, general sat. So once you have this big giant formula here, run it through this kind of transformation, and you get 3 sat instance that does the same job as that. It completely captures arbitrary Turing machines. That's the proof. It's short, simple transformation. But the reason it's simple is because we didn't have to reduce all of NP brute force the hard way, Turing machine by Turing machine, with all the transition functions and states and tape positions, and because Cook did all this heavy lifting for us. So now all we got to do is compose that with a simpler back-end transformation that bridges the gap. How many understand the strategy? And we'll use the strategy again and again. Any questions? So you see how it goes. Once you prove one problem is NP-complete, you can get many for the price of one. It's a pretty good deal, right? It's like a weekend special. You know, prove one, get 5 for free. Actually, you get hundreds for almost free. You know. And this is what I was saying about 1 sat. So 1 sat, you can look at variables and instigations. 2 sat, here I'm giving you a hint. Look for cycles in some implication graph. Extra credit. All right, so Cook did this thing in 1970. So in 1971, 72, Karp quickly came on the heels of Cook and showed what Cook showed, but not just for satisfiability, showed it for about 23 other problems, 21 other problems, some huge amount of problems. And it didn't have to look very hard for these problems. They came from all over the place, fast and furious. So Cook opened the floodgates, and Karp let the tsunami in, basically. So these are all problems that Karp showed NP-complete right after Cook published his paper. The clique problem. So I give you a graph and an integer like 4, and I ask you, is there a clique of size 4 in this graph? And I painted here in green the clique of size 4. I could have asked, is there a clique of size 6? And the answer will still be yes for this graph. There's also a clique of size 2 here. A clique is just a complete graph on k nodes. So a clique of size k is k nodes where every node connected to every other node inside the clique. Right, so here's a clique of size 5 in this graph. Now, you might think, you know, why is it so hard to come up with a clique if I give you a graph? Well, it's because when I give you the graph, it's not painted nicely to highlight the clique. That's why. Just like, why is it so hard to find a satisfying assignment in the Boolean formula? Well, that's because I don't give you the assignment when I give you the formula. You have to find it. Same for the clique. You have to find it the hard way. There's a clique of size 3. And yeah, it's amazing what you find on the web when you Google for things, you know, besides homework and midterm answers. But I digress. So if I ask you, is there a clique of size 6 here in this graph? Now it's not so simple, right? Because I'm not painting the clique for you, so you don't know where it is. It could be one subset of 6 or another, and there's a lot of subsets of 6 nodes in this graph of size, you know, what, 10 nodes or whatever. So now you see why it's, you know, if the graph has 1,000,000 nodes, well, you know, ask for a clique of size 10,000. Well, that's not so obvious at all anymore. If you start looking for all subgraphs of size 10,000, how many are there roughly? A graph of size 1,000,000. If I say subgraphs of clique of size 10,000, roughly how many are we talking about? Just order of magnitude. So the first node that you pick would be one of 1,000,000 nodes in the clique. So there's 1,000,000 options for that. The second node, how many options are there? 1,000,000 minus 1. That's almost 1,000,000. Third node, almost 1,000,000 also. Fourth node, 1,000,000 minus 4. These are all numbers close to 1,000,000. So the total number of combinations will be 1,000,000 times 1,000,000 times 1,000,000 times 1,000,000. 10,000 times. That's 1,000,000 to the 10,000. That's much bigger than Google. Or is it? 1,000,000 to the 10,000, so it's 6 times. It's a huge number. So the point is, it grows exponentially with the size of the graph and the size of the clique, right? So it turns out it's NP-complete. We'll talk more about these problems. Another problem, set cover. So given some universe of objects, and a bunch of subsets, I'm showing it kind of abstractly or diagrammatically here. The question is, are there k subsets that among them will cover the entire set? So here's a simpler instance of this. This is a more general instance. But if I have 12 objects, these 12 dots, and these subsets cover some portions of the dots, so this subset here covers these 4 dots, and this subset here covers these 4 dots, and this subset here covers these 2 dots, is there 3 subsets that together cover the entire set of dots? And in this case, there are. This subset here, plus this subset here, plus this subset here, 3 of them will cover all 12 dots. But in general, it's very hard to determine that. It's also NP-complete to figure this out. These are, I'm calling them classical NP-complete problems simply because they came very quickly on the heels of Cook's theorem due to CARP. So that's a set cover problem, and there's a cover set. Again, interesting Googling humor. So Hamiltonian cycle. I give you a graph, and I say, is there a closed tour through all the nodes of the graph that pass through each node once and only once? So this is almost like traveling salesman, except they don't even care about edge weights. It's an unweighted graph. So here's a graph, and here's a Hamiltonian tour through the nodes, and the dotted edges are not used in the tour. So is there a Hamiltonian cycle for this graph? It's not so obvious, right? So that's another NP-complete problem, Hamiltonian cycle. Graph coloring. I give you a graph and I say, couldn't you paint or color, could you colorize the graph in a way that no 2 adjacent nodes share the same color? So for example, here's a colorization of this 5-node graph where no 2 adjacent nodes share the color, right? So it's like map coloring. There's many, many applications to all of these problems, by the way. Thousands of different practical, everyday applications to all of these problems. Graph coloring is actually used by compilers to assign registers in compiled code. How many knew that? Good. I'm impressed. How did you find that out, by the way? Oh, okay, good. Yeah. And all these problems, like here are just several books on graph coloring and nothing but graph coloring. It's something that's called chromatic graph theory. Chromatic means chromatic means color-wise or color-related, chroma or chromatic. So I'm just showing you, my favorite 5 books on graph coloring, and there's dozens of others, and there's dozens of books on any one of these NP-complete problems. No kidding. They're so ubiquitous and practical, and needs to be solved every single day. NP-complete to colorize a graph. Partition. That sounds even simpler than graph coloring. I give you a bunch of numbers, integers even, not even real numbers, just integers. And I ask you, is there a way to break up this list of integers into 2 subsets that have equal sum? The sum of one is equal to the sum of the other. Sounds pretty straightforward, right? I mean, NP-complete. Yeah.
I've seen dynamic programming algorithms for this where it isn't in exponential time anymore. Why is it still considered NP?
Because the dynamic programming algorithms for it will do one of 2 things. One is they won't find the exact answer. That's one scenario. So yeah, they can run quickly, but the answer will not be the right answer. You'll be close. They'll try to minimize the difference between the 2, but the difference will not be 0 necessarily. Number 2, if they do find the exact answer, they ain't going to run in polynomial time.
Okay, so even if they make it with the whole matrix and everything, that's still not necessarily correct.
Let's just say this. There's no known polynomial time algorithm for this problem because it's NP-complete. So if you use dynamic programming to solve it, either it won't find the right answer or it'll run in exponential time. If you can come up with a dynamic programming algorithm for this that runs in polynomial time, call up the Clay Institute and get your $1 million. Plus a Turing Award on top of that. Plus a PhD from us, our gift to you. You can skip graduate school. Yeah. So it's amazing because it's so innocent looking. It's a bunch of integers breaking into two subsets that have equal sum. What could be simpler than that, right? But all of them have this kind of false innocence appearance to them. Knapsack problem. So that's an interesting problem. You have a bunch of objects. Each one has 2 parameters, a weight and a dollar amount. And you have some bag that has a total weight limit, capacity total limit. So you have to put as many of the objects as you want in the bag, respecting the total limit. This is like the airplane problem. When you come on board, you have 50 pounds total for all your stuff. I was going to say junk, but stuff. Your things is stuff. Other people's things is junk, right? So you want to respect the 50-pound limit, and if you have over 50 pounds, sometimes they make you leave stuff behind. You know, they say, well, you can't bring it on, but the plane's leaving in half an hour, so you know, you actually want to jettison some stuff. Which stuff are you going to get rid of at the airport? Your jewelry, your watch, your laptop, your 5 bottles of water. Why? That's cheap. You can easily, repurchase it on the other side for a few bucks. But if you start leaving your jewelry and your cash and your that's expensive stuff. So this is exactly what this problem is. Another way of thinking about it is, your house is burning down. You can only go in there for 5 minutes, grab whatever you want, and leave. But you only have one trip, and you can only carry 30 pounds or 40 pounds in your arms, and that's it. So what stuff are you going to take? The stuff that's at most 40 pounds total, but the stuff that is the most valuable. Right? You're not going to grab all your water bottles out of the house, right, out of the fire. You're going to grab your jewelry, your cash, your laptop, whatever is higher value. So this is trying to maximize the value given the weight constraint. And by the way, when I say value when your house is burning down, I don't just necessarily mean dollar value. It could be sentimental value. You may want to save your grandparents, black and white photo. I'm just saying, the value may vary. It's not necessary, or some Christmas gifts that your loved one gave to you or whatever, that may have higher value sentimentally, not necessarily monetarily. So the value here is not necessarily just dollars and cents. It's whatever is important to you. So that's a knapsack problem. NP-complete, amazingly. Nobody knows how to solve this in polynomial time. And you need to solve it every single day when you board an airplane. What to take in your suitcase that's less than 50 pounds, because the other stuff you can buy on the other side for cheap, so you're not going to carry it with you and go over the limit and be charged $200 because you're 2 pounds over the limit. That's really not worth it. By the way, this book is on a reading list even. You can explore a lot of these things. Some cartoons that kind of make fun of this kind of, this is a guy ordering at a restaurant, right? So he's saying, here's the menu, here are the prices. So he said, we'd like to order exactly $15.05 worth of appetizers, please. Right? And the waiter goes, huh? And so that's kind of a cruel thing to do to a waiter. You say,
This problem, what if you sorted by cost, and then you filled up the 1505, and then you have some kind of excess? Wouldn't there be some sort of swap out? That's going to be greater than P, right?
Yeah.
What's that P approach?
Yeah. So he's basically constructing a heuristic to solve this problem, an approximation scheme. So he's saying, okay, take the most expensive item. So in this case, it'll be like this $10, thing is the most expensive of these 5 items. Put that in first, and then take the next least expensive item, next most expensive remaining item that still fits with it, and keep doing that, for example. It turns out that if you do that, you won't necessarily get the optimal. This is a greedy approach. This will give you a pretty good solution in general. And sometimes it'll stumble on the optimal by accident.
Wouldn't there be a way to go backwards? Okay, now you...
Yes. So if you get stuck, you sometimes want to backtrack, but you'll find out that there are examples where you have to backtrack arbitrarily number of times all the way to the beginning and start over. And not pick.
Once you start over, it's greater than...
No, not necessarily. It's not that simple. You may never have to start completely over, but this problem is NP-complete, period. So that's a fact. That's a theorem. Now you're trying to make an end run around NP-completeness by coming up with some heuristic that will always find the optimal answer quickly. But NP-completeness theory is here to tell you won't succeed in that. You see, that's exactly the point I was making earlier. But if you work for a company and they tell you solve this kind of a problem, like how to pack suitcases real efficiently and so on, and they say go. Look up one of these classic problems, and if it correlates to what they told you to do, don't waste 6 months and $1 million of their budget trying to, in vain, solve the problem, because you will not succeed. Why? Because if you succeed, you'll be, as a corollary to that solution, you would have proven the P is equal to NP, basically, and you might as well quit that job and just get the $1 million and go retire somewhere for at least a decade. It's not so simple. It's a very good try, though. And that heuristic won't be a bad heuristic. if you actually run this heuristic that you suggested, pick the most expensive thing that fits, and then pick the next, and backtrack sometimes if necessary, and make it run in polynomial time. And if you compute those heuristic answers, those approximate answers, against the optimal answers and plot them on a graph and run statistics, you'll see that probably on average for random weights and random costs object uniformly distributed over, say, a range of numbers from 1 to 1,000, chances are that heuristic will be no worse than a few percent away from optimal on average. On average, it'll be like 98% of the optimal. And that's good. In real life, it's a win. But if you want 100%, not unless P is equal to NP. If you want 99.999%, that's probably still doable in polynomial time. Just try harder, backtrack more. You'll be spending more time, not exponentially. Because if you want to spend exponential time, look at all subsets. It's easy to do. If you want to spend exponential time, there's 2 to the 5 subsets of 5 objects, 2 to the n subsets of n objects. Try them all. See what the cost and weight of each is, and then you'll know what's the best, for sure. But that's exponential time. That's no big, clever trick. That's just brute force. And we don't have exponential time in real life, right? 2 to the 32 is already 4 billion, and 2 to the 64 is that squared, and 4 billion squared will take many decades to run. 4 billion is the number of seconds in a year. In a century, excuse me. In a century, not in a year. Question?
So this is a 0 or 1 answer. That is, you take it or you don't take
That's right. You can't split them.
And one more question I have is on how much space can we actually occupy? Because we're talking about time complexities here.
Yeah. Usually the space is not the issue. So for example, to solve satisfiability in brute force exponential time, how much space does that take? No, it doesn't. That's my point.
Linear space?
Linear space. How do you do it in linear space? Just look at all n-bit strings for all the variables. N bits, all possible n-bit strings. You can use only n bits to just click up like a counter. And every time, it's a different combination of the n variables, and you can do it in place, reusing the space over and over again. All you got to do is count from 1 to 2 to the n in n-bit space. That's it. You don't need exponential space at all. And all of these don't need exponential space either. Like this, if you want to do it brute force, you have n objects. Again, just have an n-bit string. The n-bit string will represent which object you take or don't take. And just click in place all n 2 to the n combinations of n bits. Try each one repeatedly in a loop. Reuse the same space over and over again. And in linear space, you get your answer again, n exponential time. So most of these problems can be solved in linear space. And occasionally you might need quadratic space. It's rare. But never exponential.
So
Yeah.
in what space can't this be solved in linear or in polynomial?
Repeat the question. I'm not sure I understand exactly what you mean.
We know that if you're given exponential space, then you can solve it in linear time.
What do you mean exponential space? You can't spend linear time using exponential space.
You need space. You need
The time is going to be at least as large as the space, because just initializing that space to zeros already will take you exponential time. And you better initialize the space, otherwise there'll be garbage there and you won't know what to do with it. So you can never use less time than you have space to use. And to put it another way, you cannot use more space than you have time to use. Just initializing an array of exponential size will take exponential time. Never mind doing anything more clever than just initializing it to zeros. Or searching it once. Just touching every space once will take exponential time. Right? So you want to rephrase the question?
Yeah.
Okay.
What's the best approximation for us if we don't use linear space, but you use a higher degree polynomial?
Space is usually not the issue, because the brute force algorithms that take exponential time work in linear space usually, and some of them require maybe n log n space or exponential or quadratic space. That's about it. The heuristics, they're quick and dirty solutions. The heuristics, the approximations, also take linear space. And they run very quickly. Sometimes they run in linear time or quadratic time at most. Actually, a lot of my papers were heuristics for NP-complete problems. Actually, my PhD dissertation was a bunch of heuristics for NP-complete problems, very useful heuristics. Place and route for chips and Steiner tree problems and problems that anybody can use. When you construct this building, wiring up all the lights together to the big transformer outside, it's a three-dimensional Steiner problem. Right? How many get that? Wiring up all the air conditioning ducts, all these ducts to the main blower on the roof. Steiner tree problem again, three-dimensional. Connecting all the water pipes to the main water line outside, all the sinks and toilets and faucets in the kitchens and so on. Steiner tree problem again. So when you design a building, you have to solve the Steiner tree problem over and over and over again. FedEx, you want to deliver packages in a city. Which NP-complete problem is that? Travel salesman problem. And they have to solve it every hour of every day in every city of the world, every minute that they do business. They want to pack a truck with packages to minimize the wasted space on the truck, because the truck usually is not weight bounded. The packages usually are pretty light, full of styrofoam and stuff like that, but it's volume bounded. There's no room. It's not that there's no capacity to carry weight. Bin packing. And speaking of bin packing, that's a nice segue. I'd like to say I planned it that way, but I'm not sure I can say that. But anyway, minimize the number of bins you need to stuff a bunch of packages into. So you can have a one-dimensional version. The bins are all vertical bins of the same width. And the packages are sizes, 26, 18, 8, 16, 5, 6. So they just have heights, that's it. So the question is, what's the minimum number of bins necessary to fit all the packages, given that the bin capacity of all of them is 80 and no more, right? And so you might want to stuff the bins this way. Could you use less bins than 19 bins? It's not clear. Maybe you can shift some of these things around and redistribute them. Maybe you'll get one bin less, but it's very hard to figure out. It's NP-complete, actually. Even this one-dimensional version. When else do you solve this problem, by the way?
So I was just at Disney World, and they actually have a guide there. Almost all the rides take rows of 8 people, and they try to keep every group together. And they have a guy there asking how many people in your group.
Yeah, very good. That's nice. Yeah, he's bin packing into a roller coaster or whatever the ride is. Yeah, exactly.
Break it up because they have a single rider line where they,
Yeah.
if you want to split from
Yeah.
your group.
And sometimes they'll get into a bind where there's nobody standing in a single line maybe, and there's all sorts of groups, and it's actually very hard to solve. To minimize the number of empty seats, wasted seats on the ride. When else do you solve this problem in your personal life? Yeah.
Like when you write a texture mapper, you want to minimize the amount of space that textures take on like a sprite sheet.
Yeah. What else?
When you move
Yeah, when you move your stuff, not your junk, your stuff. You want to minimize the number of boxes you need to, pack all your stuff in, and you want to minimize the wasted space in a box, whether it's books or clothes or odd-shaped objects. That's exactly what this problem is, and it works in every dimension, right? So for FedEx, it's like three-dimensional. When you move, it's also three-dimensional because the boxes have shapes, and you want to make sure they fit in your car or in your truck, and you don't have to make multiple trips if you don't have to or it's not necessary. And Tetris is a bin-packing video game, if you think about it. And there's physical versions of Tetris too. There's actually a plastic-based, physical Tetris that you can buy. And you can buy Tetris kind of bin packing kind of shelves. These are polymorphic shelves. These are all disconnected. And you can reconfigure this in different shapes. So if you want like a long vertical space for like a wine bottle here, you can put it this way. But if you want to put a bunch of little cups, you'd flip it sideways and kind of, these are nice. I don't know if IKEA sells those or whoever, but I think that's a pretty cool concept for shelving, pretty nice. So it's all kind of bin packing. But again, even the one-dimensional version is NP-complete. Never mind two-dimensional, three-dimensional, or more elaborate versions with more constraints. Other NP-complete problems are classical Steiner trees. So give a bunch of nodes, given a bunch of points or nodes in a graph, or just points in the plane, what's the smallest tree that spans all the nodes? And this time you're allowed to use extra nodes that you invent, that you add to the set. So for example, in the set of 3 nodes here, if you just use a minimum spanning tree with no extra nodes, the cost will be 1 plus 1, it'll be cost 2. But if you're allowed to use an extra node in the middle that you put there deliberately, the cost drops from 2 to 1.7, roughly square root of 3. That's just a simple example with 3 nodes. But if I give you 40 or 50 nodes, where do you put these extra new nodes that you're allowed to use at your discretion to make an overall smallest possible tree? NP-complete, it turns out. Now, the spanning tree problem is not NP-complete. It's Prim's algorithm or Kruskal's algorithm will get you a nice minimum spanning tree, optimal solution, subquadratic time, even n log n time, easy to do. The graph version of this is even harder because the weight's not going to be arbitrary, not just distances in the plane. So the graph version subsumes the geometric version. So for example, for this problem, you have to connect all the blue ones, same as here, and the red ones, the other ones, which are the reds, you can use or not use at your discretion. And now you have to come up with a spanning tree like the one I'm drawing here that connects all the blue ones and uses some of the red ones to minimize the overall spanning length. NP-complete. So that's actually one of the problems I worked on, and I have a heuristic that gives you a solution that's no worse than like roughly 1.5 times optimal for arbitrary weighted graphs, which is the most general form of this problem. And my algorithm actually holds the world's record for the best bounded solution, heuristic solution that runs in polynomial time. It won a best paper from a journal award, and it worked pretty nicely. It's been cited many hundreds of times by other researchers that use it in networks and many other applications. So NP-complete, and there's entire books written about this problem. So I'm just showing you my favorite, 4 or 5 books written on the Steiner problem. And my own work is cited in some of these books as well, which is always nice to see. It's people use your work for other stuff. And you can find them on the reading list if you want to dive deeper into this particular problem. And this is used in VLSI to connect transistors on a chip. You want to minimize wire length so you can maximize the yield because the areas of the chips are smaller, and the yield is what determines the cost of the chips and their competitiveness of your products if you're Intel or AMD. Very, very ubiquitous problem. Traveling salesman, we already mentioned that a number of times, but here it is formally. You find the shortest tour through a bunch of points, whether they're cities on the map. Google has some built-in apps, on their maps applications that allow you to kind of plan a tour through a bunch of destinations and find some traveling salesman tour through these cities if you want to kind of minimize the time wasted on the road or getting to the next destination and that kind of thing. And again, many, many books have been written on a traveling salesman problem, and this is also something I worked on as well, and I actually created a new version of the traveling salesman problem where the nodes can now move. So the targets are no longer fixed stationary points. They can move around on the map. So even if you restrict the motion to linear constant motion, they just kind of float in a vector direction with a magnitude and a direction, but don't just meander arbitrarily like ships at sea. They usually move straight with a constant speed, right? Or trucks in the desert, whatever. Planes in the sky move usually at constant speed in a constant direction for a long time, right? So if you want to pick up points and move, now it's a generalization of traveling salesman. Regular traveling salesman is a special case when the vectors are all 0. Now if the vectors are non-zero, it becomes even harder. And I have some heuristics for that. I wrote some papers on that. It came out pretty nicely. So. And you can, of course, use it to do art, like TSP art. In the algorithms course, we did some of that. Some people did TSP. How many did TSP art? There's a few of you. Yeah. It's nice. Here's a TSP through all the non-trivial towns in the United States. Towns that have a population of at least a couple of thousand people or whatever. So this is something that's called a traveling presidential candidate map. If you want to make sure you visit every single town in the U.S., this is sort of the route you'll take. And there's even cartoons about TSP and so on. So, any questions about any of these? Yeah.
For this Steiner tree problem, how many extra nodes are you allowed to add?
As many as you'd like. But if you add too many in the wrong places, it'll cost you unnecessarily extra.
Okay, so that's a cost.
Yeah. So connecting to these extra points costs you because you got to go to them instead of other nodes. But sometimes it'll help. Other times it will hurt. So there's no limit to how many points you can add. But at some point, the more you add, the more you lose. You don't win anymore. There's certainly a point of diminishing returns.
Is there
Yeah, so for example, there's something called the one-Steiner problem. That one is pretty simple. You only have one extra point. The question is, where do you want to put it? That one is actually solvable in quadratic time. So there's nothing NP-complete about that because it's only one extra point. There's only a finite number of regions you can put it in, and within those you can find the optimal, using some math, you can find the optimal place within that region to put that one single point. But because it's one point, you get some sort of monotonicity going and convexity going, and you can sort of maximize the value of that point within that region. There's only a finite number of regions, like a Voronoi diagram type situation. And within each cell, find the best place to put a point, and the answer is the best of all of them is where you put that point. So that's a quadratic algorithm, roughly. And I actually have a TSP, a Steiner tree heuristic based on the one-Steiner problem, since you mentioned it. So you can solve this in quadratic time, where to put one new point. So my heuristic was, and I invented this one as a graduate student, actually. I actually remembered the moment when it occurred to me. Find the best place to put a point. Add that point in. That will be some savings. Repeat. That's it. That's the heuristic. Find the next place to put the next point. Now that you have n plus 1 points, treat them all equally as points in your set. Find the n plus 2 point to put that in, repeat, 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 repeat. The spanning tree will keep improving until it won't. And when it doesn't, stop. It turns out that heuristic is really, really good. It won't get you the optimal necessarily guaranteed, but on average, you'll be no worse than 0.5% from optimal. 0.5%. That means this, what I just described, will get you 99.5 roughly of the win of getting good Steiner trees going. That's not obvious. I mean, I had to run a lot of experiments to come up with this statistic. It's empirical. I was also able to prove that this will never perform worse than 1.5 times optimal, guaranteed. That one is a theorem. It's guaranteed. But in practice, it's nowhere near 50% more, 1.5 times more. It's more like 0.5% more, on average, for a random point set, uniformly distributed in the unit square and so on. So it's easy to come up with heuristics. It's hard to come up with good heuristics, ones that have a mathematical guarantee and in practice perform well as empirically. So for example, traveling salesman, how does FedEx solve it? You're a FedEx driver. You have 20 packages to deliver. Where do you go first? Greedy. Go to the nearest available address, assuming your app can tell you which one it is. You don't have to like sift through all the packages and read the labels and so on, waste time. Your app could say, go there next, the closest immediate destination of the first package, whatever that may be. So you drive there, deliver the package. Next, repeat. The remaining packages, go to the nearest. It's called nearest neighbor heuristic for traveling salesmen. Turns out it's not too bad. It's not guaranteed to be the optimal, obviously, because since it's a linear time kind of heuristic, or n log n time heuristic, always find the best remaining one. But it'll perform pretty good in practice. And you can modify it so it's even a little better. Look ahead 1 or 2 times. So look ahead 2 or 3 packages. And deliver the next 3 packages in the look ahead 3 look ahead. So it's not just the next best, but the next 3 best. Look for the triple, next best triple. That will sometimes avoid nasty situations, like you having to travel across back and forth across town, because you're looking 2 ahead. Okay. So anyway, think about it. So heuristics are not hard to come by. Almost everything you do in your life is a heuristic, by the way. How do you find the best mate, to have children with, to marry or whatever? That's a heuristic. It's a very complicated heuristic. It's a lot of trial and error there. Think about it. But over time, you develop better intuition as to who you'd be more compatible with by whatever experiences you had or didn't have. And some people still don't get it right after 7 marriages and 50 years of trying. But I digress. Everything you do in life is heuristic. How do you find the best job, the highest paying job? How do you find the best graduate school to go to? Now, what does optimal even mean in that scenario? Right. For job, you can say, well, it's money. So that's a more objective criteria, the number of dollars per year. How do you maximize that? Well, most of you are running a heuristic right now for that. Why? Because here you are listening to me. What will that get you? Well, it'll help you become a better problem solver, hopefully. And if it does, then maybe you'll impress the Google recruiting team better, and they'll get you a higher salary or get you the job to begin with. And so getting an education is a heuristic for making more money and being more successful and productive, and and so on. So you're all running heuristics left and right. Every day you get out of bed, you're running multiple heuristics of all kinds. So heuristics are not hard to come by. Good ones are hard to come by. Right? Okay. Graph colorability, I give you a graph and I ask you, is it k colorable? So I'll give you a graph and an integer k, like 3, k is equal to 3. I say, is it possible to paint this with 3 colors, at most 3 colors? Here the answer is obviously yes. Here's a 3 coloring of this graph. Here's a 3 coloring of a slightly larger graph. And here's a 3 coloring of a bigger graph still, with 10 nodes in it. It's called a Peterson graph, by the way. But if I give you an arbitrary graph, it's hard to tell if it's 3 colorable or not. 3 colorability is NP-complete, it turns out. We will prove this, by the way. I don't think we'll have time to prove it today, but next time we will prove the 3 colorability is NP-complete. You can try all possibilities. That's a brute force algorithm. So again, all of NP is solvable pretty easily brute force if you don't care about time. Try all possibilities, whether it's colorings, traveling salesman tours, satisfiability assignments, whatever. Brute force is easy. Efficiency is hard. So here's Richard Karp's paper, right? 1972, roughly a year after Cook proved satisfiability is NP-complete, and it's called Reducibility Among Combinatorial Problems, single author, and this guy won a Turing Award too for this. It's such an important area. And he tells you right out of the gate what he's doing. He's very cognizant of it. We show that a large number of classic unsolved problems of covering, matching, packing, routing, assignment, sequencing are all equivalent in the sense that either each of them possesses a polynomial time algorithm or none of them do, meaning they're all NP-complete. By the way, the term NP-complete wasn't even invented then, so it doesn't say NP-complete. That was historically how we referred to this later on. But then he basically is saying that they're all grouped together, bundled together into one class of problems, all of which have efficient algorithms, or none of them do. Right? And he defines a class P. And by the way, he gives a lot of credit to Cook. He says this paper was stimulated by the work of Stephen Cook the previous year and rests on an important theorem which appears in his paper. We just proved the theorem last hour. That was Cook's theorem. Right? That satisfiability is NP-complete by embedding arbitrary Turing machine computations as big satisfiable formulas. And so that was a historic paper right there. He showed that there's nothing special about satisfiability. It's not some magic problem that somehow accidentally, coincidentally, miraculously happens to capture arbitrary non-deterministic polynomial time computations. No. It's true about dozens of other problems. In fact, now we know it's true about thousands of other problems. In fact, it's hard to pick a real-life problem that's not NP-complete. It's such a ubiquitous phenomenon, actually. And he showed us that. So Cook found the first one, and he found immediately dozens of others, and now we know most of life is like that. Just at least once in your life, you should look at this entire paper, and so I'm doing that for you now. This is the entire paper, page by page. So it says in this section, we introduce and begin to investigate a class of problems solvable in polynomial time. It talks about deterministic algorithms, and it talks about reducibilities here, right? And it says a class of languages recognizable by string recognition algorithm which operates in polynomial time is also invariant under a wide range of changes to the class of the algorithm. So he talks about the robustness of the class, right? We talked about that separately. And then he says, we complete the section by listing a sampling of problems which are solvable in polynomial time. Satisfiability with at most 2 literals per clause. That's 2 set right there. That's the one I gave you for extra credit. And he actually solves it here, but try not to look at the solution. And then he talks about other problems that are solvable in polynomial time. Shortest path, that's Dijkstra's algorithm, shortest paths, right? Matching, sequencing, linear equations, these are all polynomial time problems. But then he starts talking about non-deterministic polynomial time algorithms and problems. And he talks again about Cook. He calls this term important, and certainly is. It's an understatement. Any language in a white class NP is reducible to a specific set, which deciding whether Boolean formula in conjunctive normal form, product of sums, is satisfiable, which is what we were doing here. So he refers to that, and he goes kind of through the argument. Again, recapitulating what Cook was doing. He talks about non-deterministic one-tape Turing machine, blah, 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 which then reduces to satisfiability. Now he talks about, so he says that the following theorem due to Cook is remarkable. So he keeps saying it's important, it's interesting, it's remarkable. And this guy is a Turing Award winner, you know. So it's really phenomenal that he noticed it so early on, right? Other people didn't know it. Berkeley didn't realize the importance of Cook's theorem. They didn't remember. They didn't give him tenure, right? Which is, you know, really sad for them because he went on to another university and he won his Turing Award there. So, and so he defines satisfiability, and here he kind of states Cook's theorem that satisfiability is NP-complete, right? And then he talks about complete problems in general. He talks about if P is equal to NP, then NP is closed under complementation. That's the co-NP open problem, right? And basically, he just defines NP-completeness there without calling it that. That name came later. But then he says the main theorem of this paper, all of these problems are complete. And when he says complete, he means NP-complete. Right? He just called them complete in the same sense the satisfiability was complete, what Cook showed. And then he's just listing a long list, laundry list of problems. Satisfiability is the first. Clique, we mentioned that. Packing, we talked about that. Set covering, we talked about that. Right? Hamiltonian cycles, circuits, we talked about that. And a whole bunch of others. And the list goes on. So a total of 19, I guess 21 of them. Chromatic number, that's graph coloring, we talked about that. You know, the clique cover, you know, Steiner tree, I mentioned that. I worked on that. Matching, knapsack. Knapsack is stuffing your knapsack when you try to get out of a fire. Remember, taking all your valuables or your most valuable things to you. Partition, cuts. So he shows the rest of the paper that all of these are NP-complete. He gives proofs for all of them. Reductions from all of SAT reduces to all of these. Now, once Cook did his thing, he did all the heavy lifting for satisfiability, to show more problems are NP-complete, it becomes easier because all you got to do is show how to reduce satisfiability to one of these and then one of these to another one of these, and all the reductions begin to compose, and they're all polynomial time. So you get end-to-end reductions of compositions of other reductions that are all polynomial time, and so the composition is polynomial time, and it alleviates a lot of the heavy lifting work necessary to show new problems are NP-complete, because you can leverage on the old proofs and the old problems and the old reductions. That's exactly what he does here. And here's the schema of how he does it. Satisfiability is NP-complete. We know that by Cook. So now from that, we can show that 3-SAT is NP-complete. Satisfiability with at most 3 literals per clause. That's 3-SAT right here. And this was the proof. So the reduction of satisfiability to 3-SAT, we just did that 20 minutes ago. How many see this? And you can see this picture. So this arc is a proof. All these other arcs are also proofs for other reductions. So this is his schema of what to reduce to what. So he reduces 3-SAT to chromatic number, to graph colorability. And we will do this proof. This proof is actually not easy. We're going to do that next time. You can reduce satisfiability to cliques and so on. And then cliques reduces to node cover, and node cover reduces to set cover, and blah, blah, blah. And problems down here require 1, 2, 3, 4, 5, 6 reductions all composed together. But each one of them is relatively simple, so it's not as onerous as it sounds. And that's his schema for the rest of his paper, how to show all these 21 problems are all NP-complete. Each arc here is a proof, or a reduction, more specifically. Yeah?
Is there always a direct reduction from satisfiability to any of these instead of going through one of the other problems?
Excellent question. So he's saying, are there alternative ways to prove it, like from satisfiability, say directly to one of these with a single arc? What do you guys say to that? It's a very good question. Not only there is, there must be. It's unavoidable. Why? Because all of NP reduces to satisfiability, right? Including, these are all problems in NP. So in Cook's reduction, not only all of NP reduces satisfiability, but NP contains all of these. So all of these reduces satisfiability directly through this reduction here. So that not only there's a path, there's a direct path from all of these to satisfiability.
And it's also kind of a complete graph in a way. You can reduce one to the other.
Yes. Once you compose this transformation with this transformation with this, the whole thing becomes one transformation in a sense. So take that combination of arcs and make it a single arc from anything to anything else. So it's really, you can write the complete graph here. And there's an infinite number of problems. So yes, everything reduces to everything else. And you can think about a series of transformations all composed as a single transformation. And conceptually, it's the same thing. And if you ask the question, well, is there a simpler transformation other than this sequence of 6 transformations all composed? Yes, there are. Sometimes it's harder to stumble onto them. Just like when you try to prove some theorem, there's a brute force prove, using induction and a lot of hand waving and algebra, and it's kind of, you grind it out over 3 pages. Or there's some insight that nails it on the head, and that's a valid proof too. It's just a shortcut. So there could be many different transformations. These transformations are not unique. There's many ways to transform problem A to problem B. That F that takes you from A to B preserves membership doesn't have to look like anything particular. It just has to work. And there's often many different alternatives for that F. And they can be all different. And it can be dramatically different. In fact, there's an infinity of Fs that will work. You can almost, because you can always modify the F slightly that will make it a different F prime that will also work. And sometimes you can modify it very dramatically. Just like proofs. There's actually hundreds of known proofs of the Pythagorean theorem, all looking very different than one another. And new ones are getting discovered every year. How many realize this? So proofs are not unique. Transformations are not unique. There's many paths from places to other places. But this, historically, is the schema he used in this paper specifically in 1971. He had to do something, and that's what he did. That's the roadmap he used. Okay. And the rest are just all the arcs in this graph laid out as transformations. So I won't bother you with all the details, but here's the proving 3-sat. Satisfiability with most 3 clauses. This is 3-sat. So he says replace this big formula with a bunch of little formulas involving, these extra variables that I showed you in green and red and blue. That's what he's doing exactly here. So I did it on that slide, 15 slides ago. That's exactly what he's doing there. Here is now proving all the other ones in this big graph of reductions, showing the structure of the reductions. So he gives yet more credit to Cook for showing 3-sat being NP-complete. Now he shows a few problems that are p-space complete, equivalence of regular expressions, and equivalent non-deterministic finite automata. Those are p-space complete. And membership in NP is still open, even to this day, for these problems here. So that we know they're in p-space. P-space contains NP, but we don't know that these are in NP. We know that they're in p-space. We don't know that they're not in NP. In fact, we don't even know if p-space and NP are the same class or not. That's still open. P-space could collapse to NP. In fact, p-space can collapse to p. We don't know that either, actually. That's still open as well. Of course, NP is sandwiched between P and P-space. So if P-space and P-space and P are collapsed together, NP will collapse to both because it's sandwiched in the middle. So there's still open problems. And he says these problems are not known to be complete since the membership in NP is presently in doubt. Right? So, and amazingly, they're still open after 45 years, since 1972 or so. Graph isomorphism. He says, the following important problem in NP is not known to be complete. So here's a problem. Somebody asked a couple hours ago if, can you give an example of a problem that's in NP but it's not known to be NP complete? There it is, right out of Cook's original paper, and that's still open. Whether graph isomorphism is NP complete, we don't know. Here's an interesting example of a problem that at the time was open, but now it's closed. Primes, to determine whether a number is prime or composite. At the time, it wasn't known to be complete, but it was known to be in NP. Now, we know it's polynomial time solvable. Okay, and that's just a 2004 result, this 30 plus years after Karp wrote this paper that we're looking at. So some things have been resolved since then, others are still wide open. By the way, this is a very subtle point, but let's say it once, and we'll probably say it again. But so primes are known to be in P. Tell you what, let's leave primes alone. Let me ask you the question a different way. Is sorting NP complete? Is my question. Is sorting NP complete? How many understand the question? Just a few words, right? Is sorting NP complete? Short question. How many say yes, sorting is NP complete? How many say it's not NP complete? How many say it's open whether it's NP complete or not? Ah, that's better. Why is it open? It is open. We don't know if sorting is. We don't know if addition is NP complete. Multiplication. We don't know if multiplication is NP complete. Okay, so but we can couch sorting as the follows. I give you a list followed by another list and ask you the question, is this other list a sorted version of the first list? And now the question is yes, no. And for some pairs of lists, it will be yes. For others, it will be no. So I give you two permutations of the numbers from 1 to n. And I ask you, is one a permutation of the other? Or, is one a sorted permutation of the other? So it's not about the input size, although you're right, there's issues of input size. But let's say the input is a set of integers and the output is yes, no. Whether it's sorted or not sorted. I can just give you one permutation, say, is this a sorted permutation or not of the integers that I gave you? Now it's easy to check in linear time, right, whether a permutation is sorted or not. Just make sure it's monotonic. But the question still stands, is sorting in that version, yes, no version, is that NP complete? And we already mentioned it's open, whether it's NP complete. How can it be open? Something that's doable in linear time. How can that be NP complete? Yeah. Yeah, we don't know if P is equal to NP. If P is equal to NP, all the NP complete problems are in P, because all of NP is in P. If all the NP complete problems are in P, remember they're all polynomial time reducible to one another. All of NP reduces to any problem in P, including sorting. So everything in P becomes NP complete automatically. How many get that? Yeah.
Isn't P a subset of P?
Yes. But if P is equal to NP,
Any problem in P would be a problem in NP.
yes.
So why is it open?
Because if P is not equal to NP, sorting is not NP complete. Because NP complete problems would require necessarily more than polynomial time. Because they're the hardest problems in NP. So if the hardest problems in NP would still require polynomial time, P will be equal to NP. But if P is not equal to NP, conversely, the hardest problem in NP will not be doable in polynomial time. Otherwise, P will be equal to NP. So whether any problem in P is NP complete or not is equivalent to asking whether P is equal to NP or not. And that's open.
You're suggesting that sorting is not a polynomial time approach.
No, that's not what I'm suggesting. What I'm suggesting is this. The phrase NP complete doesn't necessarily mean it's deliberately hard. It means it's not any easier than anything else in that class. It's the hardest one for the class. But if the whole class becomes easy, that problem is easy too. And all the other easy problems, they're also NP complete. In other words, you can do the transformation. The transformation is simply don't change the problem, just solve it over here in polynomial time because it's in P. So the transformation is tautologically trivial. You see what I'm saying? Oh, okay. I knew this would expose some misconceptions in your minds. That's why I mentioned it. My gift to you. But let me give you another example. Let's say there's a group of people and you're the tallest person in that group. Okay. It's like NP complete problems are the hardest problems in NP. You're the tallest person in that group. Does that mean you're really tall? No. The group can be a bunch of small people. No, I'm not trying to be derogatory or anything. I'm just giving an example. Okay, just don't jump on me. You know, once I made a mistake in some class that said I was trying to illustrate Boolean logic, and this was years ago, and I said, you know, yes, no, true, false, Boolean logic. It's like gender, male or female, right? And oh, you know, I got so much crap for that. I didn't mean anything, you know, harmful. I just kind of tried to come up with an example off the top of my head. I never repeated that example again. You know, so you know, so tall people. So if you're the tallest person in the group, it doesn't mean you're really tall in absolute terms, right? If everybody else is, you know, a short person, you know, you could be only 4 foot high, and you're still the tallest person in the group. So satisfiability is the hardest problem in NP. So are all these other NP complete problems. Doesn't mean they're objectively hard. It means nothing in NP is any harder than them. But if they end up in P, all of NP ends up in P. As long as one of them is in P, they drag all of NP into P with them, and then everything in P becomes NP complete as well. We just didn't know it.
I understand that, but how does sorting being in NP still open?
Because whether P is equal to NP is still open, and the two are equivalent. Two statements are equivalent to one another. One implies the other.
But isn't sorting a part of P?
Yes.
Isn't
And this could be a part of P too. We don't know.
okay.
But if this isn't P, it's on the same footing as sorting. Just a higher polynomial, perhaps. Maybe not n log n, but n cubed. Maybe this is solvable in n cubed. We don't know.
But isn't P a subset of P?
Of course.
So why is sorting not in NP? And not, I'm not talking about NP.
Sorting is an NP. Multiplication is an N. You know, maybe you have something that will save the day. What do you say?
I think there was a misconception.
Let's see what he says, because he seems eager.
Confusion is that if NP is not equal to NP, like the sense of like equivalence with polynomial time reductions, that like makes sense. But if P equals NP, polynomial time reduction, that itself, like the equivalence is there, just mean everything is.
So everything in P is in NP. We know that. That's a fact. It's not a conjecture, right? Sorting is in P. That's a fact. Satisfiability is in NP. That is a fact. Satisfiability is NP complete, moreover. That's a fact too. One day, satisfiability may end up in P, although it's not likely to happen. But that's an open question. That's not a fact. That's open. But if satisfiability ends up in P, all of NP ends up in P. All the NP-complete problems end up in P. And in fact, all the problems in P now are also NP-complete. Because they're all polynomial time reducible to one another. How do you reduce sorting to multiplication in polynomial time? Don't multiply, just sort. That's a transformation. You see what I'm saying? The transformation becomes trivial if you're inside P. And that's true about any pair of problems in P. They're all transformable to one another in polynomial time. Well, that's the definition of completeness. So everything becomes P complete and NP complete at the same time because P is equal to NP. So I'm glad I mentioned that because obviously, you know, intelligent people have confusion about that. That's why I mentioned it. So multiplication can be NP complete. We don't know. How is it that multiplication could be NP complete? Well, it satisfies all the definition, perhaps, if P is equal to NP, and we don't know about that. So multiplication is NP complete if and only if P is equal to NP. It's an if and only if. So another consequence of this discussion is NP complete doesn't mean it's hard. It means nothing in that class is any easier. Just like if you're the tallest person in this group, doesn't mean you're tall. It means nobody's taller than you is all it means. Right? You could be very short. The others are just shorter. That's okay. That can happen. That doesn't contradict any statements made about this height comparison.
So in a way, since
Completeness here forms equivalence classes where things are transformable to one another and that kind of thing. So, and the NP complete and the complete problem. By the way, I don't want to keep saying NP complete. You get the idea that NP complete always ties completeness with NP. No, every class has its own complete problems subclass. You're going to talk about problems that are P complete, log space complete, exponential time complete, P space complete, and so on and so on. Right now we're focusing on NP complete specifically, but every class has a complete, quote unquote, complete core subclass for which none of the other problems in the class are any easier. But you can have complete collapses. All of P space can collapse to P. We don't know that it doesn't. In which case multiplication is not just NP complete, it's P space complete. So don't think of complete, the status of complete attached to a problem is proof that it's hard. It's not technically a proof that it's hard. It's a proof that nothing else in the class is any easier. But that's not the same thing. Think about being the tallest person in a kindergarten. Right? So you're taller than all the 5-year-olds. That doesn't make you tall, objectively. You know, it just makes you taller than all the toddlers. Okay. Or you know, you're stronger than all the toddlers. Well, that's not a trivial statement, but it's nothing to brag about either. You know, so, you know what I'm saying? Yeah. Doesn't make you really strong. You're just stronger than all the toddlers. But objectively, you can either be strong or weak, right? I mean, the world karate champion is also stronger than all the toddlers. And I assume you're not the world karate champion, right? So, I mean, I don't want to make any assumptions, but you know, it's probably safe to say, right? So that's what it means. It means not any harder than anything else in the class, but it could be a lot easier. We just don't know. Now, having said that, let me give you sort of the practical side. If you ask, you know, 500 researchers in NP-completeness theory and complexity theory and theory of computation in general, and ask them, what do you really think? Is P is equal to NP? Most of them will say, no, they're not. You know, they'll be willing to bet anywhere from, you know, $100 to $1 million if they have that much to bet. You know, they'll most likely 99% of them, or maybe 95% of them. There might be a few that might kind of hedge their bet or something and say they don't know, or they don't think that they know, or they'll say that they actually believe it's the other way around. But very few will say that. Why? Because for the last 50 years, you know, all of us tried. By all of us, I mean thousands of smart mathematicians and Turing Award winners and, you know, field medalists in mathematics and Nobel Prize winners. We're all trying to come up with polynomial time algorithms for hundreds and hundreds of different NP-complete problems, and they all failed every single time, no exceptions. And you know now from NP-completeness theory that if you succeeded for any one problem, that immediately proves that P is equal to NP. So all they do is succeed for one problem, just one time, with a polynomial time exact algorithm, and that will immediately imply that P is equal to NP, and all of them failed. That's very strong evidence that it's probably because they're not the same class. We can't say for sure. You know, Fermat's last theorem, we didn't know if it's true or not. We suspected that it was true because nobody could find a counterexample for all these centuries, but nobody had a proof either until Andrew was. So you never. The strange cases in mathematics. You know, there's some near almost identities in mathematics where something is equal to something else, parameterized by some, you know, variable n. And it's not an identity because it's not true. But the smallest counterexample has like 50 digits in it. I mean, it's really weird. How many have heard of such things? So for example, there's a second-degree quadratic polynomial. If you keep plugging in numbers 1, 2, 3, 4, 5, 6, they'll all come out primes for the first 50 or 60 numbers. But the 51st number will be a composite. And there's examples which are much worse than that. The first, trillion numbers will satisfy that identity. The next one won't. So if you say, okay, it's false for the first trillion numbers, it must be false then. Not so quickly, but it's a lot of evidence. And usually the overwhelming evidence kind of shows you the trend, but not always. So we have to be careful. But chances are they're not the same class. In fact, we believe so strongly that they're not the same class that we put entire crypto systems on the back of these problems, assuming that they're intractable. Public key cryptography, even Bitcoin, presumes that you can't break the blockchain and forge it because it uses some NP-complete problems to, do the underlying crypto to make the whole Bitcoin kind of blockchain work. And so if you can break NP-completeness by showing polynomial time algorithm from all these things, among many of your other accomplishments is you can probably become a billionaire on Bitcoin, or something by forging the ledgers and so on. And entire, sub-economies are based on the notion that it's hard to break the systems. NSA's business is to come up with, good encryptions and decryption algorithms that are based on the hardness of NP-complete problems and so on and so on, and integer factoring and other, discrete logarithms and so on. So yeah, we're betting the farm on the fact that they're not the same class, to the point of national security and economic world economies and so on. So it's not just evidence; it's very strong belief, and not just specialists, but the rest of us too. Okay, so just I guess it's probably a good place to stop. But later, next session, we'll talk about the decision versus optimization version. Why verifying an answer and deriving the answer to begin with are equivalent modulo polynomial time. That's why we talk about deciders a lot and verifiers, and not just optimizers that find an answer. Anyway, any more quick questions or comments? Yeah.
If primality testing goes it becomes even easier to linear and nonlinear,
Yeah.
then would that mean that NP factorization also becomes easier, polynomial time?
It might drop a couple of notches polynomial-wise, but right now we don't even know if it's polynomial at all. And by the way, polynomial is not necessarily efficient in practical terms. Right? If you come up with a factoring algorithm that takes n to the 100, that's technically polynomial, but practically it's exponential. It won't do you any good in trying to decipher blockchain and Bitcoin if you have an n to the 100 algorithm for factoring, even though it's polynomial. In practice, even n to the 10 is pretty bad. Even n to the 6 is not so good. N squared is okay. N cubed becomes very onerous. N to the 4th is almost useless practically for any large kind of size problems. I mean, think about the fact that 1,000 cubed is a billion, but 1,000 to the 4th is a trillion, and that's many minutes on a CPU, and that's just 1,000 to the 4th. 1,000,000 to the 4th is the square of that. That's millennia of CPU, not just minutes. And even on the cloud, it would take days. If you hijack the entire Amazon cloud, you probably couldn't solve a problem of size of 1,000,000 if it was n to the 4th algorithm. And good luck to you with hijacking the Amazon cloud. Well, you can split some hairs about whether polynomial time really means efficient in general, and for higher polynomials, not so much. But on the other hand, let me just say that if you come up with an n to the 7th algorithm for something, chances are in a year someone will come up with n to the 6th, and in a year someone will come up with n to the 5.5, and in a year, 2 years from now, after that, someone will come up with n cubed, and that's just how it goes in practice. That's happened many, many times. So technically speaking, even though the polynomial is high, once it's polynomial any old way, even high polynomial, people tend to push it down and get the polynomial degree lower and lower, and eventually becomes more and more tractable. So if any crypto system ever breaks, to the tune of n to the 20 polynomial time algorithm, that's a very bad sign for that crypto system. Whether it's Bitcoin or public key cryptography or anything else, that means probably within 10 or 20 years, somebody will push it down to n to the 4th, and in a few years beyond that, it'll be n to the 2.5, and then, way before that, it'll be broken really badly. Because some adversaries can use n cubed and n to the 4th algorithm. They have enough millions of CPUs that even n to the 4th doesn't faze them. Okay, what else? Any other questions or comments? All right, we're covering a lot of ground now, so we'll keep going with NP-completeness next time. But do read about this in the book, because this is subtle, esoteric stuff. So you should read the book section about NP-completeness, look at the wiki pages, look at other explanations on the web about NP-completeness, until you kind of wrap your mind more tightly around it. It's abstract. Now we're in deep waters, theoretically speaking. It's tricky business now. All right, see you next time.